early on this, so you might not have looked at it. Everybody good with that? Okay. Now, I kind of did a little symmetry here. So we can talk symmetry at the same time. And this time I'm looking for a positive 1 by 4, and I want the area to the right. Without even looking up in your table, what's your answer? Same as that one, right? Isn't it the same thing? Don't we have symmetry to the left and to the right of the 0? Your curve is symmetric. So this little area over here is the same as this little area over here. It's symmetric. So if I don't remember my symmetry, I can look up on my table 1.54, and I can find, did anybody look up 1.54 and then subtract it from 1? What'd you get? What, like 9 what? 99382. Thank you. Now, so when you look this up, you say, can that little area be so big? Can that be greater than 50%? I'm looking for a smaller than 50%. So I know to subtract from 1. And do I get the same answer? Absolutely. If I do it on the calculator already takes care of this part. Second bears. You're going to do it by setting your lower now. Your lower one, the one you first come to, is 1.54. Your upper one is positive 9999. Keep the standard normal curve, 0 and 1, and paste. It takes care of it for you. Don't subtract anything from 1 when you get your areas, because you set that bar to tell it where to go. So can everybody do these? And absolutely fine. If you didn't see the symmetry, look it up on the table. But know that it can't be greater than 90. It can't be 90%. It has to be far less than 50%. The in-between. What's the rule with the in-between? What do I do? Subtract what? With the z-score? The areas. So I've got 2.24 out here, and I have 1.12. I want this area in between. I'm going to subtract my areas, not my z-scores. Because what happens is, this is this one area, this is this guy's area, so this is what's in common. So if I subtract it out, I'm left with the guy in the middle. So I don't have the answers in front of me. Anybody have the area for 2.24? 9. And the area for 1.12? 8686. Thank you. And when you subtracted them? Thank you so much. So that's your area. And shouldn't that be really small? Should be a small little area. Isn't it a little tiny piece where they overlap? Absolutely. Make sure your curve makes sense to you. Make sure it makes sense. Okay. Sketching, filling in your answers. Good with that? All right. Now, we're going to put this to like little application parts, which totally is going to make a lot more sense for you to figure these out. I again wrote the properties of your normal curve on top and your standard normal curve on top. Just to take a look at these, your properties of your standard normal curve and your normal curve, really, really important that you catch the difference, because we're going to be using your normal curve now, other than your standard normal curve. Okay. So just let's take a look at this for a minute here. Your normal curve, your standard normal curve has everything your normal curve has, except that's what we've been working on. It has special conditions. It has the mean being equal to 0. It has the standard deviation equal to 1. These cumulative areas are always the same. We're still going to the opposite ends. Negative 3.49, positive 3.49. That's where your table goes to. Could I get a z-square of negative 890? Absolutely. Is it very unusual? Extremely unusual, but it can happen. This is the part we're going to here now, the normal curve. The mean, the median, the mode will be at the middle. The curve is bell-shaped. The area is equal to 1. The curve never, never, never touches the x-axis. And the inflection points are at the plus or minus 1. And the inflection point just means, as I came from the left, it looked like I was going uphill, right? It looked like I was making an upward curve. Well, I changed my mind, and I decided to make this a downward part. Then I changed my mind, and I decided to make it almost like an upward again. We don't really do anything with inflection points other than say plus or minus 1. So if they do say at the inflection point it is blah, 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 you just found out the standard deviation, because that's 1 away from the mean. So that's the only reason why we look at an inflection point. So what we're going to do is take this and go back to our normal curve. I do mine a little differently than they do. And again, I want you to do it the way I do, just because it makes it a little bit easier. To show you that these are the same, whether you put numbers here or standard deviations, wherever we find that to be, we're going to convert our values to standard deviations. So we're not going to work off of 2 curves. We're going to work off of 1 curve. Oh. My board is acting crazy today. So we are going to combine this curve, and we're putting this on 1 curve. So as a result, we're going to put the mean in the middle. We're going to put all our standard deviations down here. We're going to put all our values of x's up here. So if my mean is 500 and my standard deviation is 1, we're going to put these into 1, just like we started to do before. I need you to see the relationship between the x value and the standard deviation. It is the same exact area when we find this. This is your standard normal curve. Why do I know this is a standard normal? Because your mean is 0. Why do I know this is my normal curve? Because my mean is not 0. So when we work on a curve with an application where we have x values, which we will be having, we're going to incorporate it into 1 curve. The standard deviations go on the x-axis. The x values will go along the curve. Make sense? I need you to see them both at the same time. So when we come up with a score of 650, we should be able to put our 650 right here, and we should be able to find our z-score to be smack in the middle. I want it to relate to you for this. So I do my curves a little differently than they do. Make sense? Okay. The rest is stuff we've already kind of been doing, so it's not going to look that different to you. I don't think you'll notice that much of a difference. We're going to set up probability examples. And we're going to talk about your normal curve. All right, so if you look in your book for 5.2, I can look up what page it is. Okay, when they talk about these, see the word normally distributed up here? They will always tell you that your curve is normally distributed. In a little while, we'll discuss like when they don't have to tell us that. Generally, when your n is greater than or equal to 30, they don't have to tell you normally distributed. But right now, they're going to tell us normally distributed. And this is the steps we go through. This is on the back of your notes. We're going to set up the probability statement. We're going to sketch it. We're going to convert your x values, and we're going to determine your areas. And we're going to find that area. The probability statement and the sketch are really, really important. So we're going to put one together and work on this. This is what the second part of your quiz looks like. So a survey indicates, get some color. A survey indicates that people keep their cell phones on an average, on an average of 1.5 years before buying a new one. And the standard deviation is 0.25 year, which is a quarter of a year. A cell phone owner is selected at random. And I want to see if they have the same trend that we forecasted here. Find the probability that the user will keep his current cell phone for less than 1 year before buying a new one. Assume that the lengths of the time people keep their phones are normally distributed and are represented by the variable x. So as soon as they tell us normally distributed, we say, oh, this follows a normal curve. And we set up a sketch. Make sure you just, at least on your note page, do a couple of these with me so that you have a reference. I left you plenty of space out there. Pull out your information. I'm really only given this information, a mean and a standard deviation. So here's my mean, and my standard deviation says 0.25, a quarter of a year. So add 0.25. It's like adding a quarter. Think of money. 2 years, 2.25. Subtract a quarter. This is the sketch that I want. Put your x values along the top. Put your standard deviations on the x-axis along the bottom. They need to correspond together. Now we're going to write our probability statement. Find the probability that this user at random, x, keeps this less than a year. How do I say less than a year? Less than 1. That's all I want. Less than 1. Should my area be less than 50% or greater than 50%? Less than. Think of the application here. If the average person keeps it 1.5, this person's going to keep it less than 1. Kind of unusual that they didn't reach the average yet, right? He's getting rid of his phone early. So shouldn't I have a small percent to the left of the 1.5, right? So I look to see where 1 is. Here's my 1. Nice, because it turns out perfectly in my graph. And what is my z-score that's associated with 1? What's this z-score? The standard deviation score. -2. Okay? I want him to be less than 1. So do I shade to the left or do I shade to the right? To the left. So it's going to be a very small percentage, right? We said plus or minus 2 is unusual. Plus or minus 3 is very unusual. Think of a real life situation. If the average person is getting rid of their phone after 1.5 years, if someone gets rid of their phone less than 1 year, isn't that unusual? Right? Would you get rid of your phone less than 1 year? I always keep my phone more than 2 years. That's what my plan tells me to do. Otherwise, I get charged or whatever. But on the average, people are saving it for 1.5 years. That's my average. So 1 year is far less. Now, can I use my Z-score formula? Absolutely. Now, for some of you that got the wrong signs on these, use your graph. This is the one formula I need you to memorize. But should my Z-score be positive or negative if I'm to the left? Negative. So therefore, if this is my mean, and here's my standard deviation, if this is my x value, I want to subtract so I get a negative score. So I want the smaller minus the larger. So I have a z-score of negative 0.5 over 0.25, and I keep, change, flip, or divide it out, or whatever you want to do to this guy, and I get a z-score of negative 2. God bless. Okay. Now, find me the area on your chart to the left of negative 2. Look up in your z-score and find me the area to the left of negative 2. Didn't we say this was unusual? 5% is our cutoff. Remember when we talked about 5% being our cutoff? To be unusual, it's less than 5% of the people. The less than a 5% chance that I'm going to pick someone out of this whole group of people at random, out of the whole population, that's going to turn his phone in less than 1 year. Makes sense to you? Now, for my calculator buddies, you can do this one of two ways. You can take the calculator, and we'll do this a couple of times. You can wait till you find your z-score. So I'm going to stop at the negative 2. So negative 999. I think when I hit this too many times, that's when it jumps on me. And I'm going to stop at the negative 2. I can leave my 0 and my 1 and paste. And there's my 4 decimals. I got to just round it because your calculator is so much more exact. Okay. Or you can put it on a normal curve, which is what we're on now. We're off our standard normal because our mean is not 0 anymore, right? Our mean is 1.5. So watch what you can do. You're going to come down here. You're going to say, I'm going to still do from the lower to the, I'm going from the left and I'm going to stop. I'm going negative 999. I'm going to stop when my x is a 1. Hang in there. My mean is 1.5 and my standard deviation is 0.25. I'm off my normal curve. So now I can only use my x values in here. My x is a 1, didn't I say less than 1? My mean is 1.5, my standard deviation. Now, what your calculator does is give you the same exact area. It bypasses you having to do this formula. It cuts right to the area. You still have to give me a sketch. You still have to give me a probability statement, but it bypasses this. And it cuts right to this. It doesn't give me a z-score. If I wanted to truly know the z-score, I would have to do my z-score formula. It gives me just this answer. So if I just ask you to find the probability, I still need the sketch, I still need the probability statement, but if you use your calculator, it's going to go straight to area. Okay? Because now we're not on a standard curve anymore, we're on a normal curve. Which is why they tell you this, you are normally distributed. Does that make sense? We're kind of incorporating what you learned. We're still setting up your graph. We're still figuring out your z-score. We're just putting this all together. This part was on your quiz. That was that back page. And many of you gave it a great try, and many of you got the right answers. So, tells me also, I mean, we did 1 or 2 problems when we found the z-score. You just had to kind of incorporate your area into that. But it tells me that you're making great sense of this to be able to do that before we actually pulled it together. So that's kudos to you guys. So let's try another one. Sometimes it takes a few of these to try before you get there. The average speed of vehicles traveling along a stretch of highway is 67 miles per hour. They use the word average. So pull this out. It means the average speed on this highway that people have been going by is 67 miles per hour. With the standard deviation, you're not getting a lot of information, but you're getting the pieces that you need. 3.5 miles per hour. That's my little wiggle room, left to the right of this 67. A vehicle is selected at random. This is my X person. What is the probability that this person is violating the speed limit of 70 miles per hour? So assume that your speeds are normally distributed. They're going to tell us this. And they're going to tell us that this represents the variable x. Okay. In other words, we're using x to find our probability statement. So you're going to make me a probability statement for this guy. So how would I say this? X is greater than 70. Do I want him to be less than 70? No, I want him to be greater than 70. We'll do the equals, but not yet. Let's sketch this guy. I just need to, oh my, sketch this up. I don't have to keep adding in my head. So let's pull this together. I want you to start like this all the time. I'm big on sketches. Put your mean in the middle. Add 3.5 all the way up. And then subtract it. You're only going 3 times. Now, where does 67 fall? 67 is my average. It falls smack in the middle. Shouldn't it? Shouldn't it be my mean falls in the middle of my curve? That's where your 0 used to be. That's where your standard normal. We're on a normal curve. So our average, our mean, is going to fall smack in the middle. Where is our 70? Between what two z-scores do I find 70? 0 and 1, really pretty close to the 1, right? Do I want the area to the left or to the right? To the right. Okay. So should it be less than 50% or more than 50%? That chunk of curve. Less than 50%, right? So I'm going to use my z-score formula. Should my z-score be positive or negative? I'm on the right-hand side, positive, right? Let me put my x value over here. So if I want it to be a positive and I forget which way I'm supposed to subtract, I got to subtract so that it's a positive answer. So the larger one minus the smaller one. X minus the mean over the standard deviation. And I'm going to find my standard deviation being close to 1, but not quite 1. When I put this in my calculator, I get 0.86. We're almost there. I want the area to the right. If I look 0.86 up on my table, I get this big number, 0.8051. Could that area to the right be 80%? That's my area to my left, right? It means I have to subtract this from 1. This is why your curve helps you. So I get 0.1949. There's about a 19% chance, 19.5% chance that the person I pick at random and check their speed is violating the speed of over 70 miles an hour. 70 or more. Another way to look this up is how? How could I have looked that up? Negative 0.86. Negative 0.86. And my area to the left should be the same thing, shouldn't it? My answer is still 0.86, but my area for this would come out like that. I do it on my calculator, remember you can do it with your z-scores, or you can do it using your x values. This works so nice with your x values. So your lower is your negative 999. You're going to stop. Oh, no, sorry. Your lower is your 70 because we're looking for this area. Sorry, to the right. Your lower this time is your 70. Be careful of your upper. 9999 would work fine. I'm never going to hit this. If I had something where my mean is like 999, I might want to make my upper be a lot higher. Right? I'll just add another 9999 when I keep touching it. My mean is 67. You're not on a standard normal curve, and my standard deviation was 3.5. And do you get this? Their answer is a little bit more exact because we had to round. We had to round our z-score first of all, and we had to look up in our table. So theirs is 0.1957, which is very, very close to this one, but more exact. We have some rounding rules. We rounded right here. This caused us to round to 2 decimal places. Are we getting a little bit more comfortable with this? Tomorrow we'll work on this again. I wanted you to be able to recall what you worked on and to bring this back with you. Okay, if you have your article, guys, and hang on, because I got to see who needed an article.